Imagine a jet engine running at over 700 degrees Celsius, or a power plant operating at 200 bar pressure. Now imagine the heat exchangers in these systems, constantly battling extreme temperatures, high pressure loads, and corrosion. Traditionally, they're bulky, expensive, and limited by manufacturing constraints. But what if I told you that 3D printing is rewriting the rules? Metal additive manufacturing, AM, is not only making heat exchangers stronger and more efficient, but also lighter, more compact, and better at handling extreme conditions than ever before. Today, we're diving into the future of thermal management, how AM heat exchangers are transforming aerospace, power generation, and industrial cooling systems. We'll explore the materials, the design breakthroughs, and the challenges of scaling this technology for real-world applications. If you're in engineering, additive manufacturing, or energy tech, this episode is for you. Let's get started. Before we dive into how 3D printing is revolutionizing heat exchangers, let's talk about why they needed an upgrade in the first place. Heat exchangers are found everywhere: power plants, aircraft, space shuttles, and even the cooling systems of data centers. They transfer heat from one fluid to another, keeping systems efficient and preventing overheating. But there's a problem. Traditional heat exchangers are heavy, inefficient, and difficult to manufacture. They rely on brazing, welding, and machining, which limits their design and performance. And as industries push for higher efficiency, especially in aerospace and renewable energy, the need for lighter, stronger, and more heat-resistant exchangers is greater than ever. And that's where additive manufacturing steps in. Additive manufacturing allows us to break free from traditional manufacturing constraints. Instead of welding sheets together or machining bulky components, we can now print intricate, high-performance heat exchangers directly from metal powders. So how does this work? The most common AM method for heat exchangers is laser powder bed fusion, LPBF. It uses a high-powered laser to precisely fuse metal powder layer by layer, creating highly detailed, leak-tight, and geometrically complex heat exchangers. This means we can design lattice structures and pin-fin arrays that were previously impossible to manufacture. And guess what? These structures massively improve heat transfer and efficiency. For example, researchers tested a 3D printed heat exchanger with a pin array on the supercritical carbon dioxide side and a 3D lattice on the molten salt side. The result? A 27.6% increase in power density and 21.7% improvement in effectiveness compared to traditional designs. That's a game changer. So, where are we seeing real-world applications of 3D printed heat exchangers? Let's talk about three major industries that are leading the charge. Supercritical carbon dioxide power cycles. Power plants are switching to supercritical carbon dioxide cycles because they offer higher efficiency than traditional steam cycles. But to work, they need heat exchangers that can survive extreme pressures up to 200 bar. 3D printed designs are stronger, lighter, and more thermally efficient. Perfect for this. Aerospace and jet engines. In aerospace, every gram counts. A lightweight AM heat exchanger can improve fuel efficiency and performance in jet engines, hypersonic flight, and spacecraft thermal management. And since AM enables designs with fewer welds, it reduces failure risks in high vibration environments. Renewable energy and molten salt storage. Finally, we have solar thermal and molten salt storage systems. These rely on heat exchangers to transfer energy between storage tanks and power cycles. Traditional materials corrode quickly, but 3D printing allows us to use high-performance nickel alloys like Haynes 282, which last longer in extreme environments. The bottom line? Additive manufacturing is already changing these industries, and we're just getting started. All right, now let's talk about the elephant in the room: scalability. We know that AM heat exchangers are more efficient, lighter, and better at handling extreme environments. But can we actually mass produce them at a competitive cost? The good news: advances in automated post-processing, surface finishing, and modular designs are making AM heat exchangers more scalable. For example, researchers have successfully stacked 3D printed heat exchangers modules into a scalable 1 megawatt system. The challenges. However, challenges remain. AM materials are expensive, print speeds are still relatively slow, and post-processing steps like heat treatment and powder removal add time and cost. So, is AM the future of heat exchangers? Absolutely. But widespread adoption will require further improvements in print speed, cost reduction, and process standardization. So, what's the big takeaway? 3D printing is fundamentally transforming heat exchanger design. With optimized geometries, advanced materials, and scalable modular production, AM heat exchangers are poised to revolutionize aerospace, energy, and beyond. And we're still in the early days. As AM technology advances, costs decrease, and industry adoption grows, we'll see even more high-performance 3D printed heat exchangers in commercial use. If you found this episode valuable, make sure to subscribe, share, and follow for more deep dives into additive manufacturing, engineering, and cutting-edge energy solutions. And I want to hear from you. What do you think is the biggest challenge for 3D printed heat exchangers? Drop me a message or comment, and let's start a conversation. Thanks for listening, and I'll catch you in the next episode.